So it gives me a special pleasure to introduce my friend and the next speaker in the series of our math seminar at the math department of the University of Prishtina, Dr. Travis Schedler from Imperial College in London. And Travis will be speaking about symplectic representation theory. And so this will be around an hour or so perhaps 50 minutes, and then we can add 10 minutes for questions and comments. So thank you, Travis. It's a pleasure to see you, and thank you so much for having agreed to give this seminar talk.
Okay, thank you for the invitation. Thanks for everybody for attending here. Hopefully you will get something out of it. I do want to say that, as I typically do, I have some more information on the slides than I will have time to cover. So don't be alarmed about that. I may skip a couple of things, but I can make the slides available afterwards. Okay, so what am I going to speak about? I'm going to speak about symmetry, first of all. So a little bit about Lie groups and algebras. And I don't know the background of everybody. Does everybody know what Lie groups and Lie algebras are? Or this is a general colloquium, right? So
this is a general colloquium. I don't think you can assume that. Thank you.
Okay, I will say a little bit about that. I will say a little bit about Dinkin diagrams. So that's how you classify these objects. And then I'm going to give you some geometric constructions of them. So like projective lines, flag varieties, and some theorems about that. And a beautiful construction, the Springer resolution of singularities. And then once all of that is done, then I'll be able to outline sort of the vista for one of these research directions I'm quite excited about now, classifying symplectic resolutions. So hopefully the ideas will be clear, although some of the details will be a bit of a sketch. So let's start with symmetry. So what are Lie groups and algebras, and what is symmetry? So fundamental symmetries that arise in geometry and physics can be finite in nature. So here's an example of a finite symmetry. So here we have a triangle, right? And it has some symmetries. You can rotate 120 degrees, or you can reflect across one of these symmetry lines, 3 of them. So if you add the symmetry lines and the rotations, including the trivial rotation, you have 6 symmetries here, which includes identity. The symmetry group of those 6 elements is the dihedral group of size 6, or you could also view this as the permutation group on 3 elements. So for example, permuting the 3 vertices in an arbitrary way by rotating or reflecting. Okay, so this is a symmetry group of size 6. It's a finite symmetry group in particular. Okay, but quite frequently one has infinite symmetries. Okay, so not in the case of the triangle, but if you had a circle here, well, the circle has infinitely many symmetries. You can rotate not just 120 degrees, but 30 degrees or 35 degrees or any degree you want. So every rotation, and in fact every reflection that's centered along this origin or this center is a symmetry. So it's an infinite symmetry group. Okay. Another example would be in physics. We have the hydrogen atom. This is really important. Basic sort of example in quantum mechanics, and sort of the foundation for chemistry as we know it, is all based on what happens when you look at a hydrogen atom under the spherical symmetric electric force. And so quantum mechanically, you get some really interesting solutions of the Schrödinger equation there, which you can also derive without using the Schrödinger equation, because actually just prior to that, we had Pauli who found that just using the fact that there's a 3D rotational symmetry, in fact, there's an additional hidden symmetry, as it's actually 4D rotational symmetry, you can actually recover this information about the electron configurations and their energy levels. So, so this is really interesting. So you can get a lot of symmetry. So now let me say a little bit more precisely what symmetry is. So we're going to define a Lie group. That is, in other words, a topological group. It's a group with a topology on it that locally looks like a manifold. So locally it looks like wrong color. Locally looks like some manifold Rn. Okay, so it's not just an arbitrary group, but it sort of does not one of these finite groups necessarily, although that would be an example where it's just 0-dimensional, but it could be one of these infinite examples like this circle that's locally looks like R1. So a circle, if you zoom in a lot, it locally looks like R1. This is what you would call a 1-dimensional V group. Okay. Right, so that's what we have here. And these are there's fundamental building blocks of these Lie groups, which are the particular ones called the simple connected Lie groups. Okay, so what are those? We can take, for example, this group I really like called SL2C. And this is going to be our running example. We're going to be looking at matrices of determinant 1. Okay, so this is a matrix of determinant 1. It's do you still have my screen share? Yes, okay. Just wanted to make sure. So this is the determinant 1 matrix. AD minus BC is 1. And this is actually, it's not quite simple because it has a 2-element center plus or minus identity, but up to that technicality, this is a simple group. Okay, right. So so the key question is, how can we classify these sorts of things? Okay, and how can we classify the ways in which they act by symmetries? Okay, so we're going to try to classify linear actions of groups like this on vector spaces. And Frobenius in 1896, I think, is considered as having begun this program of understanding the ways in which groups act. So he was taking, for example, permutation groups and other groups and looking at ways that they can act on vector spaces. In 1968, when we get to the case of the simple Lie groups, Hermann Weyl found something really amazing. He proved that the finite dimensional representations of simple Lie groups are actually completely reducible, which means that they can break up into irreducible pieces. So what does that really mean? Since this is a colloquium, I just say it just means that if you so i.e. such a representation, such a linear action can be written as a product of some smaller vector spaces such that each of these cannot be further decomposed. These are what are called irreducible. There's no smaller non-zero linear subspace that's preserved by the symmetries. Okay, so this is a really important thing because a priori it could be much more complicated than that. You're not just a product of irreducibles, but you have sometimes you have a subspace preserved by the group, but then it doesn't split as a product of that and something else, and that could be quite complicated. But in the case of simple Lie groups and finite dimensional representations, that does in fact work. And so this means that in the finite dimensional case, we can actually reduce our question of classification to the simple representations, of the irreducible ones. This is not true for infinite dimensional representations. Okay, I'll say a little bit about that later. All right, so let me see how I'm doing on time here. Okay, so a useful tool to deal with these representations, because it can be quite complicated. You have a group which can have an interesting structure, and then you have its action vector spaces. So it's not really quite just linear algebra because you have this group involved, which we don't necessarily understand. So a useful tool to make the problem sometimes easier to handle is to look at what are called Lie algebras. So those are vector spaces equipped with a bracket, a Lie bracket, and this is a linear algebraic data, which sort of captures the data of the group, at least it captures most of the information of the group. And this reduces many questions to linear algebra. And also, another interesting thing about these Lie algebras is sometimes you can have more representations of the Lie algebra than you have of the group. So like, for example, some of these groups that we're looking at here will have only finite dimensional irreducible representations, but now when we look at the Lie algebra, we can get some infinite dimensional ones. And this is also really interesting if you're interested in sort of real Lie groups and other things like that, where you have a nice realization of these as representations of the group as well. Okay, so this is quite interesting. So so here's an example. Let's take A, B, C minus A, where A, B, and C are complex numbers. And so this is going to be a matrix whose trace is 0. Okay, so that's the Lie algebra associated to this group I wrote of determinate 1. So basically, what this Lie algebra is, it's essentially the derivative. It's essentially the derivative at the identity derivative, the first derivative of the group. It's this thing called, now it's just a vector space, or in other words, it's the tangent space. So if you do that for some equation like AD minus BC equals 1, you differentiate it, then now we're going to turn this equation here into a different equation, which is now just saying that the trace of the matrix is 0. So the sum of these two entries is 0. This is the diagonal entries. So what's a basis for this? It's going to be, we have 3 trace 0 matrices, 0, 1, 0, 0, 1, 0, 0, minus 1, and 0, 0, 1, 0. Those are all of trace 0, and they form a basis. This is a 3-dimensional vector space. And they, if we take their commutators, we take, by the commutator here, we just mean multiplying in either order and subtracting. So EF minus FE would be equal to this, this commutator here. Then we get these relations. So this is a very well-known example. This is the simplest non-trivial example of a Lie algebra. Really is sort of the basic building block of all of our interesting simple and semi-simple Lie algebras. Okay, so I'll get into more about that. But before I do, I just want to outline the overall classification of these Lie algebras. So there's a theorem of Cartan and Killing, and was then reinterpreted in terms of diagrams by Eugene Dinkin at the age 20 to 23. He was given this problem by Gelfand. He's a Jewish-Russian mathematician. So really young, he came up with this amazing result, which it was taking something which Bertram Costin later described as kind of an obscure result in mathematics and really boiling it down to something that everybody could understand. So he showed that all of the, actually all the simple complex Lie groups are classified by some diagrams. And so the basic one that I was talking before, SL2, that's just given by A1, right? So A1, let me write that here. A1, this is our sort of our running example. It's just, the diagram is just a vertex with nothing else. But then you can get more complicated things. We have this AR, which is already a little bit more complicated. And then we have these other more complicated diagrams. And the main point to look at is that when you're looking at this diagram, in some sense, on a basic level, it means that for every node you have here, you have a copy of this SL2 that we were talking about before at each node. And you're somehow stringing them together, building a larger group out of that. But in the case of AR, it's quite simple. These are just determinate 1 matrices of a bigger size. And these SL2s are somehow the diagonal blocks. So we're somehow looking at matrices of the form that we had before, A, B, C, D, where AD minus BC equals 1. And then we're just going to put identity matrices. So these will be corresponding to somehow these nodes here, these little SL2s inside of an SLN. And you can do the same thing to build more complicated groups. And if you've heard of some of them, they're quite interesting. So these were the ones that just have determinant 1 at the top, the SL. Now the SO, these ones here, don't just have determinant 1, but they also preserve a quadratic form or a bilinear form. That's why it's called orthogonal. So these ones are going to live inside of here, right? And these And in fact, all of these groups will live inside of SL if you have the R's matching up. So this SO2R plus 1 will live in SL2R plus 1 as well. Now SP, so these will preserve a bilinear form, preserve a symmetric bilinear form. So what's called an orthogonal form. These will preserve a skew symmetric form, what's called a symplectic form. These are bilinear forms. And then we have again the orthogonal one here. So these are what are called the classical. These are what are called the classical Lie algebras. They form these infinite series for every R. And then we have some exceptional ones here. These are the exceptional, because there's only, well, there's 3 R's here. So R, I didn't write this. R is 6, 7, or 8. So there's 3 of those, 1 of the F4 and 1 of the G2. So that makes a total of 5. So rather than infinitely many, there's only 5. So in general mathematics, when you have sort of some big class of examples, those are like the main ones or the standard ones, the classical ones, and then the remaining examples are called exceptional if you have finitely many that behave differently. So the proof of this classification largely boils down to combinatorics and linear algebra. And basically what you're doing here is you're actually classifying graphs that have a certain property. That is, if you take the adjacency matrix of the graph, the matrix that tells you which vertices are adjacent to each other, and then you take a modification of it, what's called the Cartan matrix, 2 times identity minus the adjacency matrix, then this is what's called Cartan. Let's write this here, Cartan. Then this Cartan matrix has to be positive definite. So it's a symmetric matrix because the adjacency matrix here is symmetric. I don't have any arrows. So you can talk about whether it's positive definite or not. It defines a bilinear form, symmetric, which has this property that the pairing of a vector itself is positive if it's non-zero vector. Okay, so it becomes a combinatorial problem, and you can classify these, and it's actually not that hard to do it, but I won't do this now. And of course, you could ask what these arrows mean here, but I won't get into that right now. Means it's just telling you a slightly more complicated way in which you build these groups out of the vertices, these SL2s. Okay, so let's see where I am on time here. So I'm going to move on to point 3, but before I do that, since I think I have a little bit of time, are there any questions about? So this was sort of the introduction, explaining like what my problem is. I want to understand symmetries. Is there any questions about that? I mean, there will be time at the end for questions, but if there's anything that was unclear, I'm happy to say something now. Okay, so let's assume that it was clear enough, and I will continue. I will give you some geometry.
Maybe, sorry, maybe I'll ask a question so that we can have a, yeah. So what is the relationship between Lie groups and Lie algebras? I mean, could you tell us a bit more about how you associate a Lie algebra to a Lie group? You mentioned the first derivative, etc. But could you tell us another example where it would be interesting to see how things work?
Yeah. Well, so basically, how should I say this? So yeah, so basically, let me just try to write it this way. So if we look at a group, let me just make another page here. All right. So the question is how to get, let's put it this way. There's different ways to phrase it. Let's say how to get Lie algebras from Lie groups. Well, so basically the point is you have some group here, which is some maybe complicated topological space, but it's not too complicated because it locally looks like Rn. And there's also an identity element, right? So so locally it looks like Rn is also an identity element. So what you want to do is you can say now near this identity element E and G. Well, it turns out you can look at E and you can just write a vector. Let's call this vector X. You can form little paths. Can consider little paths, which you can think about as the exponential of tx. If you're writing it inside the Rn, you could actually write this in terms, for example, there's different ways to define this, by differential equation or by power series. We have to make sense of this, but there's ways to make sense of this. So x is going to be a matrix. Let's say that this is all not just living inside of Rn, but let's say it's just living inside of some n by n matrices. Let's call this n, complex matrices. So x is some matrix, which gives you the derivative, the tangent space at E. We can consider that, and now we can take x of some tx, x of some ty, and take their commutator. This is going to be trivial if the group is abelian. If the group is not abelian, this is going to be some interesting thing. And if you write the expansion of this, it's going to look like t xy minus yx plus higher order terms. Now if I let's see, is it maybe t squared? It's been a while since I've taught something like this. So we have this explicit interesting expression we get. And so basically the commutator in a group, this commutator, whether it's abelian, whether it's zero or not, so zero if you're abelian, or identity if you're abelian, becomes this structure of commutator for x and y in here in the Lie algebra. And the way to relate the group elements to these elements here is you could think about G as exponential of x and h as exponential of y for, say, t small, for example. Okay, so this is so basically the upshot is that G is a vector space. The dimension of G is the dimension of the group G, and the commutator measures. So this commutator, again, it's a map from two copies of G to itself, measures how non-commutative or non-abelian G is. So as an example, if G is abelian, so it's commutative, we always get the same Lie algebra. It's just G is just, in this case, it's well, if I'm doing complex numbers, it's Cn, but if I'm doing real numbers, it's Rn for n equal to the real dimension of G, right? And if we take G equal to sort of the general linear group and R or C, then G will be what's called the general linear Lie algebra, but it's just all matrices. These are the invertible matrices. Because if you're a group, you have to be invertible n by n matrices, and here we're going to be all n by n matrices. And then if you're any other group, there's actually some result that says that any other Lie group under some reasonable conditions can just be viewed, well, there's a large class, let's put it this way, of Lie groups that can all be realized as subgroups of this GLN RC, and in a natural way. And then we're just taking the condition that cuts that out and differentiating it, and we still get this bracket on the subspace. So in the sort of the submanifold of Rn sort of viewpoint, Lie groups instead should be treated as subgroups of matrices, n by n invertible matrices, and then the Lie algebra is a sub-vector space of n by n matrices closed under this commutation operation. This is this xy minus yx. I don't know. I should move on, but I don't know if that's helpful. Is there does anyone have any follow-up on that?
No, I think that's good.
Okay.
Thank you.
Let me see where I'm on time. Okay, that's perfect. Okay, so anyway, if any of you have any other questions, feel free to interrupt. Like I said, I'm not going to get through everything on the slides anyway, so it's better that we all sort of understand what's happening, at least to some extent, than that I get through everything. All right, so let's do some geometry now. So that was sort of what Lie groups and Lie algebras are. Now we're going to get back to those things again, but let's talk a little bit about geometry. So there's a beautiful way to construct representations of these. Representations meaning actions on vector spaces. So as I said before, these are the things that are called linear actions. Okay, of G on a vector space. So we could think of it as G cross V going to V, a linear action. So how do we do it? First, we want to define some natural geometric objects that will allow us to construct this. So we'll define what's called a Borel subgroup. It's a maximal connected closed solvable subgroup. Okay. So what's an example of that? If we take this 2x2 matrices of determinant 1, then the Borel subgroup could be taken to be upper triangular such matrices. By the way, if we do all, but I did call GL before, G stands for general and L for special. If we did all matrices, then that would also be, if we did all matrices, if we did GL2, then we would have, we could take B if we like to be all upper triangular matrices, where A and C are invertible now, because to be the determinant 1, you have to be invertible in the diagonal if you're upper triangular. Okay, so this would be one example. And now we can define what's called the flag variety. That's just the coset space, the quotient of G mod B. It's the set of all cosets of B and G. Let me write that more formally. This is just formally the set of all cosets, G times B for G and G. So of course, if G is in B itself, we just get B back, but then we can get many other cosets. So let's look at an example of that. We can take G equal to SL2 again, and B as we had before. And what is the coset space here? Well, I claim that the coset space is just what's called the complex projective line. That means the lines, the set of lines in C2. So there's two, if we could divide it into two subsets if we like. This is not really a canonical operation, but we could divide it into the subset where the first coordinate is non-zero. So that would be a multiple of the vector 1 lambda for any lambda in C. So this gives us a copy of C here. Or we could have the lines so that the first coordinate is 0. So this is just the y-axis, right? This is just the y-axis, if we like. So that first coordinate is 0. So we could divide the y-axis and everything else. And then everything else gets identified with C. So we can realize what we have here as a union of C and another point we'll call infinity. And a sort of a standard geometric way to realize that by what's called stereographic projection is as the 2 sphere, where you put infinity up at the top and you project from infinity down to the complex plane here. Every other point gets identified bijectively with C. So we could identify this, this homogeneous space, this quotient space G mod B as lines in C2, which is also the 2 sphere. And the explicit map between coset spaces and lines is just you send a coset GB to G, the matrix, times the vector C0 for any C in the complex numbers. So that gives you a line here. So you might, in other words, it's G times the x-axis. Okay. All right. So here CP stands for complex projective space. And again, remember, as I said before, that this case, this main running example, is the simplest case in the Dinkins list. It's just where you have one vertex and no other vertices, no edges. So let's generalize this to what's called a flag variety. Well, this is a flag variety, but for n equal to 2. Let's generalize this to the flag variety for any n. That will be what you get if you take SL and C. And so that's going to be matrices, as I said, of determinant 1, right? So just the n by n version of what I had before. And the n by n version of B is just the upper triangular determinant 1 matrices. So the product of the diagonal entries is 1. Okay, and then if we take that quotient, we get a very similar thing that we had before, but instead of just lines in C2, we get are called flags. So we get inside of Cn, we have the 0-dimensional space, which is just 0 because linear. We have line, V1 is a line. Then we have a 2-dimensional space, etc., all the way up to n. And so this is called a flag variety because if you think about it as a flag. If you think about V0 as being some kind of, point, and then you have V1 as being a line that contains that point, the 0 point in this case. And then you have V2, which is a two-dimensional space containing that line. It looks, you can think of it as looking like a flag. Well, it's not really a flag because, you have a point inside a line inside of a plane, but a schematic way to draw it would be a flag. So it's called a flag variety. There's our flag. And this corresponds to an minus 1. Okay, so we have here an minus 1. That's the this line segment with n minus 1 nodes. Okay, so we observe here that G acts on this G mod B by just translating. What kind of translation? Multiplying on the left by a G gives you from one coset to another. And this is a transitive action you can get from any
Travis,
other.
can I
Yeah.
ask you, so these are vector spaces, right, of dimension? Are there any restrictions on these vector spaces, or just they have to be?
Yes, these V's can be any vector spaces, but the dimension has to be I for each VI, yes. So you have to have one vector space of dimension 0, one of dimension 1, one of dimension 2, etc. And the 0 dimensional is only one choice for it. It's the origin, because it has to, the vector spaces always contain the origin. So yeah, that's it. But any, and you take all this collection of flags, and the point is that somehow to get from one flag to another, you can change basis, which is the same as acting by G, multiplying this coset on the one hand, or changing the basis for our vector spaces here, or multiplying G on each of the V's. So this gets you from any flag to any other flag. And if you take the standard flag, which means sort of the flag is given by taking the span of the first I elementary vectors, then this B here is the thing that doesn't change it. So it's a stabilizer. So then you get, similarly to up here, we get a identification between this coset space and the set of all flags. Okay, I don't know if that answered your question. Is that what you wanted to know?
Thank you.
Okay, so observe that G acts on G mod B, which implies that G acts on G mod B as well. And I said this already, and it acts in particular on functions on G mod B. So if you have a group acting on a space, it acts on the functions in the space, again, by just moving the points, and then the values of the function are the values at the new point instead of the old one. So therefore also acts, so it doesn't just act on functions, it also acts on some slightly more technical things that you can define the space, like a line bundle or vector bundle. So it acts on sections of more general line bundles and vector bundles. And I'll get to why am I saying that in just a second. Go back to the case of CP1, complex projective space. This group G acts on the global holomorphic functions. Well, acts on global whatever functions, smooth functions. But let's look at complex differentiable ones, the holomorphic ones. This is the ones I'm most interested in. Well, it acts on those, but since this is a sphere, this is compact, if you're holomorphic on it, you're constants. The only global functions are just the constants. It acts on C, and acts on C in a trivial way, because if you act on a space and you're looking at a constant function, you get the same constant function back. So it's just a trivial representation. It doesn't do anything at all. So it's not extremely interesting. So there's two solutions to get more interesting things. You could drop the holomorphic condition, which is not what I want to do, or you could replace functions by a slightly more general object called line bundle. This is really beautiful. So you can look at line bundles, which are meromorphic functions on the projective space. So they could have a singularity at a point, a pole. Like for example, a fraction. You could take a fraction like z over z minus 1 that has a pole at 1. So it's not actually defined at 1, it gives you infinity at 1. But if we allow those functions as well, instead of just holomorphic ones, they're called meromorphic, then we get more functions. So now if we allow a pole of up to order n at infinity, we get, it turns out, an n plus 1 dimensional vector space, which you can think of as just degree n polynomials, whereas, the constant functions were degree 0 polynomials. So, so this guy here will be is degree 0, degree n polynomials. You can think about it as these global holomorphic functions on the complex plane, but they have a pole at infinity, and the order is going to be that degree. So n here. So now we get something more interesting. We get an n plus 1 dimensional vector space instead of an n dimensional vector space. And the action is quite clear. It's just SL2 is a 2 by 2 matrix. It acts on x and y by multiplying by this on this two-dimensional space spanned by x and y. So it just moves x to say x plus y, for example, and y to itself or to anything. So in whatever your 2 by 2 matrix does, it tells you in the first column what x goes to and the second column what y goes to. Now the fact is that in fact these representations are all of the irreducible representations of this G. So every single one can be given in this manner. It's a really amazing thing. So now we get to what's called the Boyle-Vey theorem from the 50s, maybe around 1950. For G complex semi-simple and V a finite dimensional complex G representation, it turns out that there's a unique line bundle on this generalized flag variety. By the way, I said that this G mod B, I called this a generalized flag variety because the actual flag variety is the SLN case. It looks like this flag here. Okay, so for G complex semi-simple, for any finite dimensional irreducible representation, I forgot to write that here, then there is a unique line bundle up to isomorphism so that if you take the sections of the holomorphic sections as line bundle, you get the representation back, okay? So that's the thing. Now, is there any questions about that, by the way? So this is explaining this observation at the end, that in this fact, we get all the finite dimensional irreducibles, and in fact, it turns out this is a much more general phenomenon. So this happens for every semi-simple complex G. Is there any question about that? So in this case, it's quite simple because all the line bundles are these O of n's that I'm talking about. And they give you exactly the irreducible representations. But and for more general G, you could have more line bundles than that, but it'll still be true that you get exactly all of the irreducible representations this way. Okay, so it's a geometric construction of all the irreducible representations, and it's quite amazing because the algebraic combinatorial way of classifying irreducibles is quite it's beautiful, but it's a little bit involved. Involves some combinatorics, some keeping track of things, and here I was able to give some kind of a geometric description of everything. Although, of course, if I get down into the details of what are all of these line bundles and what the sections look like, we'll still have these complications, but I can give a global description using geometry that is not available otherwise. Okay, so now fast forward 30 years to Beilinson and Bernstein in 1981. It's really amazing. They extended this, which was about finite dimensional representations, to infinite dimensional representations as well. And as I said, we're going to do that for the Lie algebra. The Lie algebra has, in general, can have more infinite dimensional representations than the group. And the price of all of this is that you have to replace line bundles by D modules. What is a D module? It's algebraic systems of differential equations. So let me explain what's going on there briefly, because I want to get to the new stuff. But what's going on here is I'm gonna sketch this here. So if we take SL2C, which was this trace zero matrices, instead of considering a line bundle on it, we could consider differential equations. Maybe in a way this is easier to understand than a line bundle because it's just something that looks very explicit. We can take a differential equation. For example, the first one is saying derivative. So this is just on one variable because CP1 is one dimensional. And let's work on C, in fact. So just a differential equation, one variable, derivative is 0. So what are the solutions if derivative is 0? It's the constant functions, right? If df dx is 0, then f is constant. So we just get C here again. Or we could take a different differential equation where we say instead of differentiating giving you 0, multiplying by z gives you 0. Well, of course, there are no functions with that property that multiplying by z gives you 0 unless they're already 0. But there's something slightly more general in a function that has that property, which is called the Dirac delta function, if you've heard of it in physics. It's not actually a function at all. It's mathematically, it's what's called a distribution. But we call it the Dirac delta function. It's something that it makes sense to differentiate, to act by differential operators, and to call this a solution. So in either case, as modules over all differential operators, these generate something interesting. The constant function, if you act by differential operators, you get all polynomials. And the Dirac delta, if you act by differential operators, you get, basically it looks very similar, but all the derivatives of the Dirac delta. Now I'm just going to say that instead of differential operators, we can view SL2C as living inside of differential operators as the differential operators of order exactly 1. We just have a del Z, and which are well defined in the whole Riemann sphere, complex projective line. And then these give you very famous irreducible representations called Verma modules or Verma representations. So the first one is reducible. It has the constants inside. The quotient is irreducible, though. The second one is irreducible representation. These are called Verma or dual Verma, depending on your point of view. Okay, so I'm not going to go into more detail about that. Just to giving you a sketch, if you didn't understand it, just know that by looking at something a little more general, differential equations instead of line bundles, now we can get more interesting infinite dimensional representations. Any questions about that before I move on? So I need to tell you about the spring resolution and then a little bit about the current state of affairs in this field. So what is the spring resolution? Well, I'm going to try to take what I just did with Borelvay and flag varieties and stuff and try to put it into more general context. And the context is the following. So representations of the Lie algebra can be viewed as modules over some algebra called the universal enveloping algebra. So you don't have to know what it is, just it's the quantum mechanical version of just polynomials on the Lie algebra on its dual. Okay, so it's a theorem, which is part of this Beilinson-Bernstein that I said before in the SL2 case, that if we take differential operators on the complex projective line, then we get some algebra, which is basically looking at all representations. So that the modules over this are all representations of the Lie algebra on which this Casimir element, this particular central element, acts by 0. So this is kind of technical. So I'm going to, if you haven't seen this before, don't worry about it. Just on the basic level, we're going to think about two things. We're going to think about representations of Lie algebra as being a quantum mechanical version of polynomials in the Lie algebra, and differential operators on a space as being a quantum mechanical version of the phase space, T star X, so Hamilton's phase space. If you're looking at classical and quantum mechanics, Hamiltonian mechanics says that a phase space should have a position and a momentum coordinate, which gives you something kind of like double the size of your original positional space X. And then differential operators is sort of a non-commutative quantum mechanical version. Why do I say non-commutative? It's because this Z and differentiation, multiplication by Z and differentiation don't commute with each other, right? So if you differentiate and multiply by Z and then subtract the other order, you get the identity, maybe minus identity, so like that. Okay, so this fact that they don't commute is basically the Heisenberg uncertainty principle, saying that one of these is like position operator in quantum mechanics and one is like momentum operator. But if you don't know any of that, just think of all this stuff as saying that representation theory we've been talking about before can be viewed inside of the world of quantum mechanics as a quantum mechanical version of something which is classical, which is geometric in nature. So with this in mind, now I can tell you, so again, if you didn't understand the details, don't worry, I'm going to say something precise now. It's Springer's theorem, and then again in the case SL2C, and it's saying that if we take the cotangent bundles as this phase space of position and momentum for the Riemann sphere, for the complex line, I call it the Riemann sphere because of this interpretation as a sphere, so it's also called the Riemann sphere, this CP1. So it says that if we take the cotangent bundle and we take its global functions, then we get an interpretation as a quotient of polynomials on the G. And what is this interpretation? These are the functions on some subset of matrices, which are the square zero matrices. This is what's called the nil cone. So what Springer actually proved is that there's an amazing map from this cotangent bundle of the Riemann sphere, and here's the Riemann sphere here, it's a sort of doubled version of that, positioning, that's a position, then we add a momentum, and there's a map from that to just matrices, but satisfying a condition that they're square zero. This condition being square zero, if you're already trace zero, like we were before, it's saying that the determinant is also zero. So it's a standard fact. If the determinant and the trace are zero for a 2 by 2 matrix, then it's square zero, and conversely. So this, what Springer discovered is that there's this amazing map connecting them, that you can view this cotangent bundle as pairs of a point in the Riemann sphere, or a line in the plane, and a square zero matrix who has that inside its kernel, so that it takes L and sends it to 0. And if you look at those pairs, that gives you a model for this cotangent bundle. And if you project a pair to just the matrix part, the A, then you land inside of the square zero matrices. And this map here is what's called a resolution of singularities. So if you take anything which is not the 0 point, so if you take the 0 point, of course, any line is in the kernel of that. But if you take any other square zero matrix here, the kernel is rank 1, right? The kernel is rank 1 if you're not 0. So that means that this L has to equal the kernel. So that means that we're 1 to 1 over everything other than 0. So we get something which is birational. It means it's injective over a dense open subset. And it's also projective, which means that these fibers are compact. So of course, the fibers are all points except over this 0 where we get the whole Riemann sphere, but that's compact, as we've said before. So this is projective and birational map with a smooth source. And that's what's called a resolution of singularities. So they're really famous in algebraic geometry. And as a particular consequence of that, it means that every function on this phase space, T star CP1, factors uniquely as a function on this cone, this square zero matrices. The global functions on this, the same as the global functions on that. And that's a version of this Beilinson-Bernstein result that we had here, which is telling you that global differential operators on CP1 are given by some similar quotient, but the quantum version of what we were just saying. So Springer found well before Beilinson-Bernstein the classical version of their theorem, which for general semi-simple G says that if you take the cotangent bundle of this flag variety I was talking about, and you project it to the matrix part, which is a nilpotent matrix. Nilpotent now means its sum power is 0, but not necessarily. This means that sum power is 0. The size the matrix will always do. Then this projection map is actually a resolution of singularities. So it's always going to, of course, the source is smooth, the flag variety is smooth, and the target is not, it's a cone, but this is going to be projective and birational. So the global functions of the two are the same. And Kosten said, identify the global functions in the nilpotent cone with something that generalizes what we were talking about before for the SL2 case, some quotient of polynomials by explicit ideal, which is the G invariant polynomials, the conjugation invariant functions on matrices in the case where G is consisting of matrices. So summary of all this is we have the classical picture, which is Springer's picture, which is you take a phase space in classical mechanics, but for the flag variety as your position, then that has this close relationship to nilpotent transformations in the Lie algebra. It's this resolution of singularities. So they have the same global functions. And this is a classical version of what I had said before about Beilinson and Bernstein, which is relating differential operators in the flag variety to some natural quotient of the enveloping algebra. So this identifies solutions of differential equations or modules over the differential operators more precisely with representations, but now possibly infinite dimensional of the G. So this in particular includes this Borel-Weil theorem. It's a very special case, which I think is a little bit more understandable. This Borel-Weil theorem is a bit more understandable, even though it involves line bundles. So that's a special case where your D module, your system of differential equations looks like just sort of differentiating in any direction is 0 anywhere. So that gives you something that looks like the solutions are locally constant functions in some sense. So so that's the theorem here. And then Andrei Okunkov, responding to all of this, realized that you could get all of the representation theory, all of the interesting algebraic structure of symmetries, and the basic building blocks of all linear symmetries. You could get it all out of a very special geometric construction called a symplectic resolution. So Andrei Okunkov made this famous quote: "The symplectic resolutions are the Lie algebras of the 20th century." He said that. And he said, well, that's 21st, sorry. The 20th century would be the original thing, and this is the 21st century. So, so 21st century, he's suggesting we should look at other symplectic resolutions, not just the Springer one that I just wrote down. So, so this motivates the classification question Now I'm already at 50 minutes. Let me just say just a little bit about this joint program. They'll take a few minutes, and then I'll take questions. This is a joint program with some collaborators of mine, Gwyn Bellamy and Alistair Craw and others. And the goal is to try to classify the more general examples than this Springer case here of symplectic resolutions. And then we're going to understand at some point their representation theory. So let me just say I have two cases where we can give the answer to this. So I just jump to the point here. So one of the cases is where you take, instead of this nilpotent matrices, you look at a quotient singularity. You take C2n, 2n dimensional space, because we're symplectic, we have to have position and momentum, and take the quotient by a finite group. That means take the orbits under a finite group. And then many authors, I can't list them all, but ending with my collaborators and myself to some extent, we've sort of classified when these admit a symplectic resolution. And the fact is that although there's gazillions of groups, gamma, that are any gazillions of finite subgroups of this, in particular, any finite group of matrices can be thought of, if they're n by n, as living in symplectic transformation of 2n by 2n space. So of all of those gazillions, there's only a product of a few cases where you have a resolution. So one of the cases is a symmetric power of a two-dimensional singularity. This can be viewed as a quotient of 2n dimensional space by a Reith product group. This is Hn symmetry product Sn. This H here has to be a symmetry group of a Platonic solid. Basically, this is understood either cyclic dihedral or symmetry of a Platonic solid. And then you pass to this 2-to-1 covering of that. So it's called the binary tetrahedral, icosahedral, octahedral groups, and dihedral and cyclic groups. So those are the examples that you have. So this is sort of the main case, because there's for every n and every h. And the h's that you can get here are labeled also by these same diagrams. The h's are labeled by the same Dinkin diagrams I had before, but extended. You add one more vertex. So there's gazillions of these, and we can understand all the resolutions. So actually, it's a theorem of my collaborators, Bellamy and Craw, 2 years ago in Invenciones, what all the resolutions of these are. And they're all given by what are called Nakajima quiver varieties. That's some moduli spaces of representations of a quiver. So the quiver is the one that you get from this diagram, but now moduli space consists of, at each vertex, put a vector space, put some transformations between them for the edges. And then you define some moduli space, which gives you a realization of this quotient, which can then be resolved by looking at semi-stable representations instead. And then there's two exceptional cases in dimension 4, one with a binary tetrahedral group, and one with this interesting group, which is a combination of the quaternionic and dihedral groups of order 8. These are exceptional cases discovered by my collaborator Bellamy, the first one in 2009, and then we discovered together in 2013 this last one here. And this is a full classification up to 45 cases in dimension 4, which we still have to check or eliminate. Okay, but the point is that except for this second one here, this first one, we can resolve it by quiver varieties, by this Nakajima's construction. And recently we proved that we can also resolve the third one by the same construction. So since I don't really have time, I just tell you that you can identify that with a quiver variety for this quiver with 6 vertices, 5 external ones and 1 central one. So we're able to resolve them. And finally, since all the resolutions we have here, almost all of them are given by quiver varieties, one can ask what happens for the more general quiver varieties. You can take an arbitrary graph, not just one that gives you a finite quotient. And so, so Gwyn, Bellamy, and I proved in Selecta that there's an explicit classification when a general quiver variety, which graphs can admit a symplectic resolution. And they're a product, again, of indecomposable factors. And then now in progress with Alistair Craw and Gwyn Bellamy, we'll classify finally all the resolutions of all of these things. And it just comes down to an explicit hyperplane arrangement in some n-dimensional space, which is n is equal to the number of vertices. And then you just vary the stability parameter and the complement of a hyperplane arrangement. And the resolutions are then in one-to-one correspondence with chambers of this hyperplane arrangement up to action of some Namakawa Viola group. Okay, so sorry that was a very fast at the end, but that's all the time I had. So thank you for your attention.
Thank you very much, Travis, for this very interesting talk. And of course, I mean, the end was supposed to be a tour de force. So do you have any questions? Does anyone have questions for Travis? And Travis will be kind enough to send us his notes after the talk, if that's
Yes,
possible. Yeah,
I
so
will
that we
send-
can. Yeah, and so can you just scroll down a little bit when you mentioned the Nakajima exactly here, the quivers
yes.
and
Yeah.
yes.
Yes, I didn't
So
explain what they were, of course, but these are some moduli spaces. Is that the question?
yeah, and then if you scroll just a little bit down, a bit further here, and please continue just some more down here. So yes, so in this case, the extended Dinkin quivers. So you said that here I can see ADEs. I can only see the simply laced ones, right?
Yes, that's it. Yeah. So so I said it was the same quivers, but in fact, here we're really only seeing the simply laced ones at ADE. So if you wanted to, so because we're talking about representations, and representations mean it's an amazing thing, which if I had more time, I could give a whole lecture on it, but at least. But if you take these diagrams, you can try to do something interesting with them, and that is consider sort of the moduli of representations of the diagram. So instead of the group or Lie algebra associated to it, which is a completely different thing, you can just take the diagram itself, put a vector space at each vertex, and a linear transformation between them, and see, well, like, what is the set of all such things up to isomorphism. And the amazing thing is there's this amazing theorem called Gabriel's theorem, which says that for these Dinkin diagrams, forgetting about the ones with the arrows on them, so the simply laced ones, A, D, and E, Dinkin's theorem says that those are the ones, or Gabriel's theorem, I'm sorry, says that those are the ones, these Dinkin diagrams, where there's only finitely many isomorphism classes of indecomposable representations. Everything is a sum of indecomposables, and there's only finitely many of those. And if you have any larger diagram, then there's going to be infinitely many indecomposables. So that was Gabriel's theorem, but it's about just the diagram. There's no room in the statement for what you would mean by having an arrow. But there actually is a way to add the arrow into the picture, but then you have to consider slightly more nuanced type of representation. Instead of just attaching a vector space to every vertex and transformation between them, maybe you want to attach like a module to each vertex, and maybe you want to work over a non-algebraically closed field, and you want to allow it to have some division algebras entering into the picture, and that will be and then basically then this folding of a ADE into this non-simply laced type can be viewed as having to do with this passage to division algebras, and then passing from an algebraically not closed field to its extension, or looking at modules over some rings instead of just over a field. So there is actually a way to put that into the picture, but I'm not doing that here. So what I'm saying is just ordinary representation. So then only ADE are appearing here. But it's already enough to give you all of these quotients. The C2 mod H and their symmetric powers, the wreath products, are all given by these ADE diagrams. And then again, our theorem about quiver representations, this is all just the ordinary picture. So we're not allowing any non-simply laced diagrams to enter the picture. But you could generalize to that and construct some other interesting spaces that way. Is that the question?
Yes. So thank you, Travis. Thank you so much. So I don't know if anyone wants to pose a question to Travis, but I would like to thank you again. Maybe Hamdi?
Yeah, sorry. So I was wondering, so you said it's a variety, right? So
Yeah.
Is it like a projective smooth variety, or like is there some sort of like divisor like theory on these
Yeah.
varieties? Because
Yeah,
it
so
sounded to me like it was like a bit like the Grassmannian, but I'm not sure.
yeah, so you're asking what are these quiver varieties like? Is that it?
Yeah, sort of, yes.
So well, so it's kind of I didn't go into much detail this at all, so I didn't really say much at all. But this is kind of a doubled version. These are symplectic. When they're smooth, these are symplectic. So that means that they're in particular of even dimension, even complex dimension. If smooth, right? And so and in nice cases, they will be smooth for generic theta. And I didn't say what theta was either, but it's a stability parameter. So depending on what theta is, it says we don't look at all representations, we look at the stable ones. Okay, so but anyway, what I want to say is that so examples include, so if we let Q be a line, so a type A, we have to actually do something a little bit more general. We have to consider what's called a framing here. So we're only going to let the group be the product of the other. We're not going to act by the group at that one vertex. So you have to add a framing. You can get rid of the framing if you want to replace this framing by a 1 and put n arrows from it, but let's forget about that. If we take this type A, we can get lots and lots of interesting spaces. So this includes, so if we look at just representations of this quiver up to actions of GL, no, not doubling, so not symplectic. Then we can get Grassmannians. We can get projective spaces. We can get Grassmannians. The projective spaces would be where this n, the number of vertices, is just 1. Actually where n is where n is 1 and alpha 1 is just equal to 1, it's just lines. We could take the Grassmannian, and this would be p n minus 1. So we could take the Grassmannian of k-dimensional spaces in n. This would be the case again where so I think I have to say this is m here. So this will be m is 1, sorry. And this will be the case where m is equal to 1 again, but now k is alpha 1. So you can get Grassmannians and projective spaces forgetting about all of the rest of this, just looking at only those 2 vertices, the and the framing and this alpha 1. So just 2 vertices only will get you projective spaces and Grassmannians. As you might guess, if you look at these more general type A, you can get in particular flag varieties and partial flag varieties where we have not the whole flag, but maybe only some of these subspaces I was talking about before. But you can get lots and lots and lots of moduli spaces this way. But basically, you're looking at sort of isomorphism classes of what you putting any vector spaces here and any linear transformations between them. And that's this moduli space here. And then the quiver variety is a sort of a symplectic doubled version. So just last thing I say about that is that, so this is the so just to complete what I was saying. So this is this variety here. This is the undoubled one, and then the doubled one is then the symplectic version. So instead of representations, we look at the codented bundle, and then we look at a symplectic reduction. So we look at the moment map being 0. Again, I don't have much time to say what it is, but it's some symplectic thing which is sort of double in the dimension, and so you can think about these as representations of a double quiver. These are certain representations of a double quiver where now we have, say, n, we have arrows going 2 ways, so we have more transformations, and we put a condition on it, and then we can get moduli of that. So then this will give you now T star P n minus 1 in the case where we just have n and we have a 1 here, or more generally t star, the Grassmannian, if we have an n and a k here. Let's say k less than or equal to n. And similarly, there's no partial flag varieties. These are not going to give you these generalized flag varieties when the G is not SLN. It's only going to give you the actual flag varieties, but it will give you lots and lots of other things that aren't flag varieties or generalized flag varieties at all. So in particular, this will also give for the extended, for Q as extended Dinkin, as I already said, we can get M0, Q, and alpha could be, if you pick things correctly, this C2 mod H, and M theta will be its minimal resolution of singularities. For surfaces, for dimension 2, it's a theorem that there's a unique minimal resolution, which will be symplectic here. So there's only one of them to count in that case. But when you go to higher dimensions, you have many, many of them. And then these hyperplane arrangements will tell you, will label them for you. That makes sense. The chambers of the hyperplane arrangements will label the resolutions by varying the theta. Does that help a little bit?
Yes, thank you very much. Actually, this is very helpful. I've seen some sort of tropical analogs of partial flag varieties, which has been done like last year. So I was very curious how you would like obtain like basically what sorts of varieties can you come up with this way. So yeah, thanks very much.
I don't know too much about the tropical version, but yes, I guess any algebraic variety like this you could consider a tropical version. So I guess there's a whole tropical story related to this.
Yeah, it's sort of like you want to sort of like bring everything to combinatorial data, and then you work with some sort of polyhedral objects, and some information is preserved in such a way that you kind of can answer questions about the classical problems. Yeah, thanks very much.
Yeah, no problem. Any other questions? I just stopped the share just so I could see you better, but are there any other questions? I know it's late, so maybe most of you. So.
Yeah, so maybe thank you so much, Travis. It's a pleasure to see you via Zoom, and thank you for your talk, and looking forward to maybe hosting you here physically.
Yeah, that would be great.
Yeah, so thank you so much again, and thank you to the two brave soldiers who weathered the storm until the end, Hamdi and Arbor. So
yes.
Thank you. And
well, I still have to get on my flight back now. So
yes, yes. Thank you and all the best. Yeah, see you soon.
All right.
Bye bye.
Thank you for this.
And thank you. Bye.